non-linear programming problem. Yeah, programming methods are available. For solving NLPP. So an NLPP with the non-linear objective function non-linear objective function and linear constraints. So such type of NLPP is known as quadratic programming problem. Quadratic programming problem. In short, we write as QPP. Quadratic programming problem. So basically, we understand this: the objective function in quadratic programming problems are in non-linear form, and the constraints all are in the linear form. Is known as the quadratic programming problem. So the basic formulation we write as the quadratic programming problem can be expressed as maximize of fx, maximize the objective function, that means fx, which we write as summation j equal to 1 to n cj xj plus 1 upon 2 summation j equal to 1 to n and summation k equal to 1 to n xj d jk xk. So this is the objective function which are in the form of non-linear and subject to constraints are given in this form: summation of j equal to 1 to n aij xj, which is less than is equal to bi, less than equal to bi, and decision variables we write as all xj are greater than equal to 0, non-negative variables. So here we write as I is equal to 1 to m and j we take as 1 to n. So this is for quadratic problem. We can express it this way, that means we have objective function which are in the linear form and having less than equal to and all decision variables are being positive. Noted? Manshi, Meenakshi, Shifali. Okay. So, okay. Okay. So we have to remember all previous methods. That means we have used Tucker conditions and Lagrange multiplier method. So we write as Tucker condition. So the necessary and sufficient condition the necessary and sufficient condition for an optimal solution of quadratic programming problem with objective function of maximization type maximization type and linear constraints and linear constraints can be obtained as so we write this way. That means we have a maximization type of objective function and as linear constraints, that means a ij xj aij be the coefficient of xij and less bi. So here we solve the problems when we understand the formulation, what we make the formulation of the problem and solution. So there are two methods to solve the quadratic programming: Wolf's method and Beal method. So you understand the formulation. So this is our structure of the NLPP. That means which is the quadratic QPP. Here we understand the QPP. That means objective function is maximization and constraints are in linear form. So first we write as Tucker condition. So Tucker condition, we already study the necessary and sufficient both conditions. So the problem is less than equal to. Here we see that the problem is having less than equal to sign. That means we introduce the select variable. So we write the steps. So you remember all the steps. So introduce select variables. Select variables which are non-negative select. That means Si sphere form. And Rj square. Rj square in constraint R solve problem to linear programming problem. But now in quadratic programming problem, we use this decision variable. You understand this? That means we write as all the decision variables are greater than equal to 0. Now we involve these decision variables to solving the quadratic programming problem. So we make one equation. That means you can give, this is the equation second, and the decision variables, this is the equation number third. So this is the equation number third. So when we are going to introduce select variable, that means si square. So si square select variable for less than equal to problem. But here we introduce rj square. Rj square means for constraint problems. That means such type of problem. We that having greater than equal to sign. So we make this equal to less than 0. That means minus xj less than equal to 0. So we introduce rj square in constraints second and third. So we give the equations here. So in constraints second and third, second and third. So the problem modifies as so this problem modifies to minimization. That means minimize of fx, this equal to summation of j equal to 1 to n cj xj plus 1 upon 2 summation of j equal to 1 to n summation k equal to 1 to n xj dk and xk djk, sorry, djk and xk. So djk and xk, and subject to constraint. Now we write the subject to constraint in this way. That means summation of sorry, j equal to 1 to n aij xj. So we write as summation j equal to 1 to n aij xj, or we introduce select variable, that means si square. So convert in equality form. So here we write as I equal to 1 to m, and decision variables we write in this form minus xj, and we add rj square, which make equal to 0. So here j equal to 1 to n. Understand? So here when we introduce select variables for both, that means constraint as well as decision variables, and the problem reduced in minimization, sorry, maximization, yeah, modifies as this is maximization problem, sorry, maximization, maximization. So the problem reduced in this form, just we write objective function as it is, and constraints are changed. So constraints are changed, that means write in the form of bi, that means equal to bi and equal to 0. So here we involve the decision variables for solving the problem. We also involve the decision variables. So we make another equations on the basis of decision variables. Okay, noted, Bhavna? Okay. Now we Lagrange function. So first, this is the part of Tucker condition. We write here as, so we introduce select variable. Now the Lagrange function. The Lagrange function L. So we write in this way. That means how many variables are there? So one is x. X means x1, x2, x3, xn variables. Second is s. S for slack variable, non-negative slash si square, and another is r. R we use the decision variables make equality, and another one is lambda, and another one is mu. Uh, uh, what is the role of mu? The role of mu as a multiplier, but this multiplier used with the decision variables only. Lambda used with constraints, and mu is used with the decision variables. So this is also the multiplier, but we use with the decision variable equation. So you can understand. So we write as this equal to. So that means first we write the function, that means fx, function fx minus constraint, means we write as summation of I a11 aij xj plus si square minus bi. We write to this form minus summation j is equal to 1 to n mu j on the basis of this mu j. So we write as minus xj plus rj square, minus xj plus rj square. So we make a Lagrange function on the basis of constraint and decision variable. Fx, this is the function fx here. So function, we put the value of the function. That means the value of the function is summation j equal to 1 cj xj, summation j equal to 1 to n cj xj plus 1 upon 2, summation j equal to 1 to n, summation k equal to 1 to n xj djk and xk minus summation j equal to 1 to n lambda I aij xj, this is x, aij xj plus si square minus bi and minus summation j equal to 1 to n mu j minus xj plus rj square, minus xj plus rj. So this is the Lagrange function. Noted? Bhavna, Vibha. Okay. So to derive the Tucker condition, differentiate Lagrange function and Lagrange function partially with respect to its constraint variable and put or equate to 0 each partial derivative, equate to 0 each partial derivative. So when we differentiate, that means with respect to x1, x2, x3, how many variables are there? So the first equation, then we differentiate this with respect to xj, so gives us cj minus summation of k. When we differentiate with respect to xj, that means xj to 1, so k equal to 1 to n xk djk and minus xj. We differentiate with xj, so summation j equal to 1 with respect to xj. So xj1, that means I. So I equal to 1 to m and lambda I aij plus si square constant 0, this 0 and only first term, this term. So all are 0. So we only this term, and when we differentiate this one with respect to xj, so minus xj is 1, minus minus is plus. So this one is plus, so this is mu j. This is mu j equal to 0. So we know that j value of j is 1 to n. And when we differentiate with respect to s, differentiate with respect to s. So when we differentiate with respect to s, so the gives this term only, that means second term. Other terms are 0, will not involve the s. So this can be written as minus 2 lambda s, minus 2 lambda s. So this equal to minus 2 lambda s, 2 lambda s equal to 0. That means s lambda isi, or you can say that lambda you write as lambda isi general form. So lambda I into si, this equal to 0. So this is the first equation. That means again we give the first equation, this is the second equation, this is the second equation. And for third equation, or we can write this as or lambda I si square is equal to 0, or we can write as lambda I summation of aij xj minus bi is equal to 0. So this is the equation number 2. That means we obtained this, we differentiate with respect to si. That means this equation, you understand, this because this involve only si. So with respect to si, when we differentiate this, and another one, when we differentiate with respect to mu, with respect to r, now we write it again with respect to r. So we differentiate with respect to r. So r involved in this term only, so this one. So that means we write as minus 2 mu r equal to 0, or this is for single, and for general term you write as mu j rj equal to 0, or you can write as mu j xj equal to 0, mu j xj equal to 0 uh, for j equal to 1 to n. So this is the equation number 3. This is the equation number 3. This is for single element, this is for general case, and this is for mu j xj. So we have decision variable xj form. That means this is the xj, mu j xj, and again we differentiate with respect to mu. With respect to mu. Another variable are mu. So here x, s, r, lambda, mu. Lambda, okay, sorry, we differentiate uh, with respect to lambda. Now, first we differentiate with respect to lambda. So we differentiate with respect to lambda. So lambda involved in this term only. That means this is the third term. So with respect to lambda, so lambda I. So you see that we write as summation of j equal to 1 to n a I j x j plus s I square minus b I equal to 0. Minus b I equal to 0. Or you can write as summation j equal to 1 to n a I j x j is less than equal to b I. We remove this variable. That means this is the equation number 4. This is the equation number 4. And for this equation, we differentiate with respect to mu. So when we differentiate with respect to mu, so equation gives us, we differentiate with respect to mu. So this gives us minus xj rj square. So minus xj plus rj square is equal to 0. So xj greater than equal to 0. So we write as j equal to 1 to n. So this is the equation number 5. So this practice we done all the questions to solve the quadratic programming problem. So this is the general formulation. So we write here all the variables are non-negative. All the variables are non-negative. So that means the variables means we are talking xj, si, rj, lambda I, mu j, all are greater than equal to 0. We involve 5 variables. With respect to 5 variables, we differentiate this. So first we differentiate with respect to s. That means first with respect to x, this one for x, you can write here differentiate with respect to x. So this is for x, second for s, third for r, next for lambda, next for mu, and all this. So the conditions, that means second condition, lambda I si is equal to 0. This is the second condition you have to remember. This means lambda I si equal to 0. Condition 2, lambda I si equal to 0. And third condition you have to remember mu j xj. Mu j xj equal to 0. So are called complementary slackness conditions. Are called complementary slackness condition. So these two equations are called complementary slackness conditions. So lambda I si equal to 0. Lambda I si equal to mu j xj equal to 0 implies that the variables xj, μj and si cannot becomes the basic variables. Becomes the basic variables simultaneously. So you remember the word basic variables when you solve the problems, that means solve the linear programming problem by using simplex method. So we construct the table of simplex method. So we write first column as the basic variables. First column as basic variables, then xb, cost of the basic variable, then cb, cost of the basic variable, then xb, then y1, y2, y3, yn, and on top we write the cost, and bottom we take the row of the delta j, and we make the last column for the ratio, and make pivot and etc. We do all things. So same we are moving modified simplex method known as the Wolfe method. Wolfe method which solve the non-linear programming problem. Non-linear programming problem. So you understand here we write the basic variables. So basic variable, that means these three cannot take place simultaneously in the basic variables. That means if xj in the basic variable, that means mu j and si not in the basic variable. Okay, so now the other variables, the other conditions, that means condition number 1, condition number 4, condition number 5, and condition number 6 are nothing but linear programming constraints contain 2n plus m variables. 2n plus m variables. So you have to remember complete procedure, because we when we solve the problems we use these 5 numbers directly, 5 conditions directly. That means first condition, this is the first equation, this is the second equation. So maximum use we of the lambda I si equal to 0 and mu j rj equal to 0. This is the equation number 3. And you have to remember this. That means xj, μj and si cannot becomes the basic variable simultaneously. So you remember all things, that means incoming vector, outgoing vector. So when xj is outgoing vector, then you can make incoming of si. So si on the basis of incoming, when xj is outgoing. So all three cannot be taken in same table, take place in the